Welcome back to sqadia.com, ladies and gentlemen. My name is Mohammad Osama, and we are talking about probability and distribution in medical statistics. And this specific lecture is about central limit theorem and conditional probability, in which we are going to talk about central limit theorem, conditional probability, and Bayes theorem as well. So let's start off with central limit theorem. It is a very important mathematical theorem and expression that links normal distribution with other distributions in a unique and surprising way, and is therefore very useful in statistics and medical research as well. So the sum of a large number of independent random variables will follow an approximately normal distribution irrespective of their underlying distributions. If we have a very large sample, so that's why it is important that we sometimes say that increasing the sample size can actually move us towards a normally distributed data or a normal distribution, and that sometimes we also do in our research when we want to do a parametric analysis on the normally distributed data. So this means that any random variable, which can be regarded as the sum of large number of small independent contributions, is likely to follow a normal distribution. So what are the advantages of using a normal distribution? The main advantage in using the normal rather than the binomial or Poisson distribution is that it makes it easier to calculate the probabilities and confidence intervals. And talking about the consequences of central limit theorem, let's start off with the binomial distribution. So the normal distribution can be used in approximation or as a substitute to the binomial distribution when n, which is actually the sample size, when the sample size is very large. In practice, this works if n, the probability of n or probability of 1 minus p are both greater than 5. So where n and n1 minus p are number of successes and number of failures. So if they are greater than 5, then we can use the normal distribution instead of binomial distribution by the use of central limit theorem. So here let's take a look at the distribution of the binomial distribution, and here we can see that we have 3 histograms, and the possible outcomes are n is 0 and 1, which means we have 2 possible outcomes or number of successes. And similarly here we have 3 different, and n is equal to 2 and n is equal to 1, and here we have n is equal to 4 and we have 4 different you can say bars or lines. So as we can see that when the n is increasing, here n was 1, here is n is equal to 2, and here n is equal to 4. As the n is increasing, we can see that this binomial distribution is becoming more and more symmetrical, and it is starting to resemble a normal distribution. So increasing n can actually help us in using normal distribution instead of binomial distribution, because it starts to behave and act and look like a normally distributed data. Now, moving on to the consequence of central limit theorem, talking about Poisson distribution and how we can use normal distribution instead of Poisson distribution. So the normal distribution can be used as an approximation to the Poisson distribution, or as a substitute to Poisson distribution, as the mean of the Poisson distribution increases. So if we increase the mean of the Poisson distribution, then we can actually use the normal distribution by applying the central limit theorem. In practice, this occurs when the mean is greater than 10. So let's take an example here. So here we have 3 different graphs or distributions, and here the mean is 1 because 1 has the greatest probability. Here we can see that the mean is 5, and here we can see that the mean is 25 between 20 and 30. So you can see that this does not look like a symmetrical distribution or a normal distribution. This somewhat starts to look like it, and this pretty much looks like a standard normal distribution, because as we increase the mean, the Poisson distribution starts to look like a normal distribution, and that's what is the consequence of the central limit theorem. As you can see, here we have these bins. So when we start to increase the mean, and then this, you can see this structure of bins start to mingle with each other, and it starts to look somewhat like this inverted bell distribution, which is the normal distribution. As you can see here, we have increased the means and it started looking like this from this. Now there's another thing or phenomena which is known as conditional probability. A conditional probability is a probability of one event happening given that another event has also happened. To take an example of this, let's say that we wish to know the probability that a patient has a particular disease, given that they have a positive result on a diagnostic test. Which means if a person had a positive result on a diagnostic test, then what would be the probability of that person to have this disease? Now, this conditional probability can be calculated using Bayes' theorem. What is Bayes' theorem? We will going to take a look at that in the next slide. But before that, it is very important to know that the underlying probability of having the disease is a different thing as compared to the probability of having the disease when you have a positive result. Similarly, it is different that the probability of having a disease when the result is different, when the result is positive, is different from the probability of the result being positive when the disease is present. So it is very important to understand because these are different things. And looking at Bayes' theorem, it would actually help us better understand that. So Bayes' theorem enables us to reverse the conditional probabilities. And for example, we have two events, A and B. For example, either the disease, there is the disease or there is no disease. So we have two events, for example. So probability of A, B means that the probability of A happening given that B has already happened. Let's take the previous example, that probability of the disease to be present given that the test has already been positive. So this is often shortened to the probability of A given B, like the probability of disease given the result is positive. So the probability of A given B is not the same as the probability of B given A, as I already mentioned in the previous slide. The probability of B given A means that the probability of the person having a positive test when there is a disease. So these two are not the same thing. These are entirely different things. So that is very important when we are talking about Bayes' theorem and conditional probability. As I already mentioned here, the same thing. Moreover, if we want to calculate the probability of A given B, which means that the probability of A when B has already happened, or if we talk about that previous example, that probability of the disease to occur when the test has already been positive. So we need to put in the probability of B given A into probability of A as an individuality and the probability of B. Probability of A means that the probability of disease, and the probability of B means the probability of the test to be positive. So we put all these probabilities, and then we can use this Bayes' theorem formula to calculate the probability of A given B. And this is very useful when we have a conditional, you can say, scenario. So that was all about probability and distributions, and I hope you learned something new out of it. So keep on watching sqadia.com for more lectures like this. This is Mohammed Sama signing off. Thank you very much.